Okay, if you're still with us here, we're on section 3 of measurement and calculation. So what we are looking at on our book now is we're looking at significant figures, which is good. Looking at insignificant figures is just really a waste of time due to their insignificance. So we're just looking at significant figures, and we're going to take a look at some scientific notation and math operations with both significant figures and scientific notation. Okay, so we do have some rules, and I apologize for the clip art here in our list of rules here, but we have some rules for determining the number of significant figures. And the number of significant figures are going to be important because they're going to tell us how accurate we can report our answers in lab. So that just because we type something into the calculator like that last answer we saw, and we get like, in that last podcast, we were calculating density, and we get 2.41315, well, what we could not do is we could not keep all of these numbers in that previous answer because our data that we were given was not accurate enough to maintain that type of answer, or to justify keeping that type of answer. So we have to be able to determine our significant figures so that we know whether or not we can report our answer to what degree of accuracy. So let's look at our rules. Rule number 1 is that if our data has non-zero numbers, well, all non-zero numbers that are reported are significant. So 1,742 is 4 significant figures. Those are all significant. This is 3 significant figures. So if they're read directly off an instrument, they are all significant if they are non-zero numbers. That's pretty easy. That takes care of 9 out of 10 digits. Now we just have to look at zeros, right? Zeros are the problem. Zeros are sometimes significant and sometimes not. Zeros that are to the left of a non-zero number, zeros to the left are never significant figures. Notice though it's saying they're simply holding a place. So zeros to the left, never ever significant. Okay, so notice this is only one significant figure. It's just measuring to the thousandths place there. It's one significant figure. This has 2. Notice the second rule about zeros says any zeros that are sandwiched between non-zero numbers are going to be significant. So my rule about this one here is this is my sandwich rule. If they're recorded via the instrument between 2 non-zero numbers, they are significant. So this is 4, this is 3, because those zeros are in between. Now, this is the only really tricky bit of all of significant figures rules. So one, all non-zero numbers are significant, right? Zeros that are sandwiched are significant. Zeros to the left are not. So left, right, are not significant. Sandwiched ones are. So we just get down to readings to the right of the non-zero numbers. Now, they're only going to be significant if a decimal point is visible. So notice 170 only has 2 significant figures. That 0 is a holding place. 170 with a decimal on has 3 significant figures. As soon as a decimal comes into it, it makes those zeros significant. And this is kind of, you could think of saying, well, I have $1,000 in the bank. That could be an estimate. That could mean $1,000. So that's just an estimate. The only significant figure in that is the 1. Or you could say, I have exactly $1,000. That would be 1,000 with a decimal at the end. That is saying exactly $1,000. That is 4 significant figures. So it's the difference between kind of giving an estimation and giving the actual value. So we can look at here a couple more examples that are on the sheet. So if you want, you could kind of pause the podcast and try these, write them on a piece of paper, see if you could figure out the number of significant figures. I'm going to go through here and try each one myself. So notice, again, we have a 0 at the end of the number. That end 0 is only significant if there's a decimal there. So since there's no decimal, it's just saying 540. We're unclear about that last decimal place, so this is only 2 significant figures. The next one, same exact rule. Here we only have 3. And number 3, same thing. It's 200. It's not 200 exactly. There's no decimal at the end. There's nothing to tell us that's an exact recording. Only that is 200. That's only 1 significant figure. Now, again, all non-zero numbers are significant, so this is 2. Again, zeros to the left are only placeholders. They're just telling us where the value is. It hasn't been measured to that value, so it is just a placeholder. Notice in scientific notation, if we're in scientific notation, all the values represented here are going to be significant. And they're going to be significant for another reason. these zeros follow a decimal. If zeros follow a decimal and a non-zero number, then they are significant. So in 5 here, this has 4 significant figures. We can ignore this because that's just telling us where the decimal is. This is the actual recorded value. 6 should be easy here. It's 2. And then notice I'm skipping some, coming back over here. Notice all of these are non-zero. Again, we ignore the exponent because that's just telling us where the decimal is. This is 4 significant figures. 2. Take a second here on 13 if you haven't yet to figure this out. But notice again, the zeros to the left are never ever significant. They're just telling us where the decimal is. But our non-zero number is, as are the numbers to the right that follow a non-zero number and a decimal. So if again those zeros to the right are after a non-zero number and a decimal, then they become significant. So that has 3, 14 has 4, 15, 3, and 16 again, 4. So here's a good summary of our rules. These zeros to the left are non-significant. They're only telling us where the decimal is. They're not readings. They're telling us where the decimal is. Notice all of our values that are non-zero are significant. So the 4s and the 5s are all significant. These zeros are significant, like it says, because they're between non-zero numbers, are sandwiched. And then the zeros at the end are significant because they follow a decimal and a non-zero number. So this value would have 1, 2, 3, 4, 5, 6, 7 significant values. So this has a high level of accuracy in this value. So now we need to look at, when we're doing math operations, how many digits do we keep? How many significant figures do we keep in our answer? Well, first off, if we're doing addition or subtraction, we actually don't look at the number of significant figures. Even though we were just talking about significant figures, we actually look at the decimal place. And we keep to the least accurate decimal place. So whenever we're combining data, we always can only combine we can always only keep the least accurate piece of data. Or how do I want to say this? Let me restate that. Our answer can never be more accurate than the data that we're given. Okay, so what that means is if we have this number 4.8 and we subtract 3.965, well, we can't report our answer out this accurately because we don't know the digits in this 4.8. We did not measure them, we did not know them, so it's inaccurate to report our answer to that level of accuracy. So our answer cannot be more accurate than our least accurate piece of data. Our least accurate piece of data only went to the 10th place. So we have to round our answer off at the 10th place, and that is all that we can keep. Okay, so this is adding together a bunch of numbers. Notice this goes to the 100th, this goes to the 1000th. So again, our first step is we're going to add up all the numbers we're having. We're not going to ignore those numbers. They were values that we recorded, so we are going to include them in our calculation. So we are going to add everything up, punch it all into the calculator, but then when we get that value, again, it cannot be more accurate than our least accurate piece of data. So this is only going to the 10th. This is our least precise number. It's only 1 digit after the decimal, so our answer can only be 1 digit after the decimal. Notice what we do here, though, is if I'm going to cut it off there at the 8, I do have to look at the number behind it and round it off if necessary. So the 8 followed by 9 means if it's, again, 5 or greater, we have to round it up. We round it up to 9, and that is our answer. Okay, now our rules are going to change because we're looking at multiplication or division. In multiplication or division, we do have to count our number of significant figures before a math operation. So notice this has 2 significant figures because the 0 follows a decimal and a non-zero number, so it has 2. This has 3 significant figures. Now notice what they're doing. They're dividing these 2 numbers. So 3 times 10 to the 4th, or times 10 to the 4th, and 1.15 times 10 to the 4th, they get this huge number, and this is exactly what we're talking about, that just because we get a huge number on the calculator, we can't report that as our answer. That's saying that we knew our answer down to the, tens, hundreds, thousands, 10,000s, 100,000s, millions, what's after millions? Million, 100ths? I'm actually not really sure. But we don't know our answer that accurately. All we had was 2 significant figures in our least accurate piece of data. So again, the answer cannot be more accurate than our least accurate piece of data. In this case, multiplication and division, we're looking at significant figures, so there's only 2. So our answer can only have 2. We round it off after the first 2 significant figures, and our answer reported accurately is 2.6. So if we look at a density problem like we were doing in the last podcast, notice our mass balance, gives you a lot of accuracy, a lot of significant figures. This one gives 5 significant figures. Notice the graduated cylinder they used gave only 2. So they take their mass, they divide it by their volume, and they get a number. And it looks really accurate, 1.02496, but it contains 6 significant figures. That would be, again, more accurate than either of our pieces of data. We did not actually measure the density of that substance that accurately. Since our least accurate piece of data has 2, our answer can only have 2. Notice what we do. We have to round it off. Just leave the first 2 significant figures, and it becomes 1.0. So that 0.0 is very important because it's saying, yes, we know accurately down to the 10th place that the density is 1.0. We don't know it beyond then because that's the limit of our significant figures in the values that we had. So this is going to be very important. So if we go back to that problem we did from the last podcast, what we had here is we had, I won't move it, 482.63. We had all this accuracy in our mass, but our volume was only measured to 200. And notice the scale, again, only goes up by 100. So that's as accurate as we could measure it. So when we got 2.413 something 15, we got all of this accuracy, 1, 2, 3, 4, 5, 6 significant figures. Our mass answer only had 5. Our volume answer actually only had 1. So really the level of accuracy we could report for the solid is just 2 grams per milliliter. And this is going to be very important when we go forward into our laboratory calculations, that we don't assume that we are more accurate than what our data gives us. Okay, so a quick kind of reminder on scientific notation. I'm sure we've done this before in other classes, but again, we're going to use it in chemistry, so we're going to talk about it in chemistry. So we use scientific notation to have a good way of expressing really large numbers or very, very small numbers. So notice this is the distance from the Earth to the Sun in meters. Notice that's a lot of zeros. And so what we do is we move the 0 up behind the first non-zero number. So, and then we count the number of places we move it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we move that 11 places. So in scientific notation, we'd include, again, all the non-zero numbers. We wouldn't drop any significance in our value. And then we go times 10 to the 11th meters. So it's telling us where that decimal is. It's 11 places out behind the first non-zero number. Just the opposite action if we're talking about really small numbers. Again, here we have the wavelength of green light in meters. Notice a very small number, lots of zeros. So what we do is we move that decimal the opposite direction, 1, 2, 3, 4, 5, 6, 7 places. So now we moved it backwards. So we moved it at -7. So in scientific notation, the wavelength is 5.10 times 10 to the -7th. So one more quick example of scientific notation. We have a number. We want to represent it in scientific notation. We have to move that decimal 1, 2, 3 spots, right? So our answer, when we look at it, if we've moved it 3 spots, and that's to the left, so that means our exponent is going to be positive. So it's 5.3266. We keep all the digits because they're significant in this case. We only drop non-significant zeros, and our exponent's to a power of a third. Now we want to look at math operations with scientific notation because we can do quick, easy math operations with scientific notation. We can do multiplication and division. So notice what it says for multiplication. If we're going to do multiplication, what we are going to do is we're going to take that problem and we're going to deal with it separately. So if I zoom in on this problem here, let's look at the problem. Notice what they're doing. We have 2 times 10 to the 7th times 4 times 10 to the 5th. What we can do is we can break that up and we can multiply the numbers in front by themselves. 2 times 4 is 8. And then what we can do is add the value of the exponents. So if we have 10 to the 7th times 10 to the 5th, well, when we're doing that, that means in multiplication we add the exponents. So 7 plus 5 is 12. So that ends up being a really, really easy calculation. For division, it's the opposite. We can still separate things, right? So if we're dividing 2 numbers, we can still separate things. We can do the 2 in this case. It's 2 times 10 to the 7th divided by 4 times 10 to the 5th. So we can do 2 divided by 4. That's 0.5, right? Now our exponents, though, in division is we subtract them. So it's 10 to the 7th divided by 10 to the 5th is 7 minus 5. That gives us 10 to the 2. So 0.5 times 10 to the 2 is 50. Or if we wrote this in standard scientific notation, it would be 5 times 10 to the 1, right? Okay, so best way to figure out how to do this is just to look at examples and to try some for yourself. So here we have 9 times 10 to the 8th divided by 2 times 10 to the 2nd. And what do? Well, we divide out the coefficients themselves, the numbers in front. 9 divided by 2 is just 4.5. So what we've done is handle those coefficients in front by themselves, and then handle the exponents by themselves. And again, if we are dividing exponents, we're subtracting the exponents. So 8 minus 2 is 6, so 4.5 times 10 to the 6th